Okay, so we're going to proceed to the first science mission talk of the Formosa 8. So the talk will be given by Professor Alfred Chen from NCKU Taiwan. He will present the mission entitled the studies on atmospheric electricity, ionosphere physics, and high energy physics by dual band imager of atmospheric transient and electron temperature and density plot. Okay, so it's your turn, Professor Alfred.
Hi, good morning, everyone. This is Alfred Chen from Chen University. In this talk, I will give an introduction to the scientific panel of the Formosa A, first Formosa A satellites. In these missions, we will put two instruments to have studies on atmospheric electricity, ionospheric physics, and high energy physics. Okay, so in this talk, the Formosa AA and the science panel will be briefly introduced in the first section, and I will pay more time on about his science objectives, and then give us some introduction about the instrumentation, and then give a conclusion. I suppose in the first presentation, Dr. Chen should be give us some parameters for Formosa A, but unfortunately I didn't see live, so I spend a few minutes to add this information on this slide. This is the configuration of the Formosa A. This satellite will be placed in the orbit of 561 kilometers with an inclination angle of 97.64 degrees. And it is a sun-synchronized orbit with a local time of 10 to 11 a.m. The payload location, in the beginning, NSPO provided 3 possible positions for the science payload, and the NCKU team chose this location on the Z direction. So this is RSI, and this is the position of the science payload they allocate for the payload. And in this position, they also have some restriction for the science payload. The size cannot exceed 20 centimeter by 10 centimeter by 10 centimeter, and the weight should be less than 2 kilograms, and the duty cycle should be keep less than 36%. The orbital average power should be less than 1.8 watt. And this payload should keep power off when it is not in operation. So therefore, this payload should be turned on and off every orbit. So this also brings a lot of difficulties in the design of the mission. As mentioned by Professor in the last talk, previous talk, and the resources allocated for the payload is very limited, and only one payload also bring a lot of difficulties in the design of the science mission. Even like the NCKU team finally proposed for the payload with this jet, and we have equipped with 2 micro camera we named DIAT, dual band images of atmospheric transient, and we also have a TNEP, which is used to measure the electron temperature and the density. And this is a red direction. So therefore, the TNAP will face to the red direction, and the camera will point to the nether direction. Okay, I give us some information about the payload first here, and then we will have some more discussion in the later slides. Dual band imager of atmospheric transient in Chinese, 双波段大气瞬变影像仪. It's a 2 CCD micro camera, can take up to 30 frames per second with a field of view 20 degree by 20 degree. And with this FOV, the corresponding to the spatial range is about 200 kilometers by 200 kilometers. And the resolution is also listed here. It's a spatial resolution by nether direction can be up to 0.4 kilometer per pixel. And these 2 images are equipped with special designed filter. The first one is the N2 LBH band. So his wavelength covered in the 220 to 280 nanometer. This is ultraviolet band, and this is intermediate bandwidth, about 6 nanometer. And the other one is also equipped with oxygen 1, centered on 630 nanometer. It is a narrow band filter, so it is the bandwidth is only have 3 nanometer. And the TNAP is used to measure the electron temperature and the density. So this is density profile, electron density profile at the daytime and the nighttime, and either for the solar minima and the solar maxima. According to these figures, we can know that the electron temperature density will vary from 5 to 10 to 8, 3, 10 times to 1 to 10⁵ per cubic centimeter. And the electron temperatures can range from 500 Kelvin to 500 kelvins. Okay, so this is some parameter we use to design the mission and the instruments. So in these missions, totally we will have 4 colleagues, faculties from NCKU, including Zhu Shujun, Lin Jianhong, Yang Yi, to join this mission. And then we also have a science team and the engineering. The members coming from the physics department, earth science, and the department of astronaut and the aeronauts. The science objective of this mission is we will focus on the three topics. The first one is terrestrial gamma ray flash, also known as TGF, and the atmospheric transients. And the second one is global ionospheric electron density and the temperature monitoring. And then the third one is air glow and the equatorial plasma bubble observations. So we can have two cartoons to show about the terrestrial gamma ray flash and the atmospheric transients here. I will give us more elaboration on these topics later. And the EPB is also a very important topic, which is now observed by Formosa 7. So we can find that the 3 topics listed here is not new topics to the Taiwan's space science community, but also the heritage of the Formosa 2, Formosa 3, and the Formosa 5 and the Formosa 7. So with this instrument, we are trying to continue the existing research on this field. Okay, terrestrial gamma ray flash, also known as TGF, was first reported by Fisherman et al. In 1994. They reported 12 unexplained terrestrial flashes observed by Compton Gamma Ray Observatory. This satellite is originally designed to monitor the gamma ray burst in astrophysics, but they accidentally find from their catalog, they figure out the 12 some flashes coming from the atmosphere. So it is a rare type of a high altitude electrical discharge above the thunderstorm region. And according to the analysis, they are originated in the atmosphere at the altitude above at least 3 kilometers. And the time of these events lasts only 0.2 to 3.5 milliseconds. So we can find this is the light curve of this basic terrestrial gamma ray flashes. So this is the 12 events reported in 1994. So it is very short. And the peak energy from few MeV to 20 MeV. So the photon spectrums of this event are very, very hard. So it is indeed a gamma ray and consistent with the boson emission from MeV electrons. And the follow-up studies from Stanford University in 1994, they successfully linked TGF to an individual lightning stroke, occurring only within 2 milliseconds of the TGF. So it is a very strong evidence that this TGF have a very strong association with lightning. But Betsy only detected 77 TGF events in 10 years observation. So after light and more gamma ray satellites was launched, placed into the orbit. And this gamma ray satellites not only detected, monitored the gamma ray burst in astrophysics, but they also put attention on about the terrestrial gamma ray flashes as one of their scientific tasks. Okay, so in these slides, we will see RASI also observed the TGFs, but they observed the TGF with much higher energy than those detected by Betsy. And according to observation observed by RASI, they estimate that more than 50 TGF occurred on the Earth's surface every day. And the Fermi Gamma Ray Space Telescope have a more accurate observation. They estimate about 500 TGFs every day globally, but some of them was go undetected. So we can see this is the statistics of the gamma ray detected by the Fermi. So the black portions indicate the gamma ray corrected the terrestrial gamma ray flashes, and the green is gamma ray burst. So therefore, they collected a lot of gamma ray burst, terrestrial gamma ray flashes for the further studies. And I have to also mention that this 500 terrestrial gamma ray flash per day is indeed it is a very low rate comparing with lightning. Now we know lightning occurrence rate is about 46 flashes per second globally, and that means we will have 3 to 4 million lightning events per day on average. So this rate is relatively low, and more terrestrial gamma ray flashes collected by the following satellite missions, and the geographic distributions also indicate a strong correlation with lightning. So we can see this drawing. This is these figures. The Fermi gamma ray flashes was shown in this one, and this is they checked the EMP pulse, which is terrestrial gamma ray flash associated their location, and the lower panel indicates the lightning density, which is constructed by GLD 360 global lightning detection network. So we can find that the strong correlation of the distribution of the terrestrial gamma ray flashes is perfectly overlap with the lightning distribution. So this is also give us some ideas of if we will have to find this kind of terrestrial gamma ray flashes, we have to pay more attention about the tropical or subtropical areas, which is, and the lightning regions, three lightning channels here is also the sum of areas. If we program the missions, we have to pay more attention for the TGF survey. So another thing is have to take into account is the mechanism of this kind of high energy photons. The detail of the production mechanism for TGF is still uncertain. And these TGF photons we are presumed that are emitted by electrons traveling at with speed of light, and the light collided with the nuclei of atoms in the air, and then release their energy in the form of gamma ray. So now the favored model is a relativistic runaway electron avalanche. We also name it REA. So that means it indicates large population of energetic electron can be formed by the growth of driven by quasi-static electric field. And this quasi-static electric field is provided by the lightning. So when the lightning was triggered in the cloud or around the cloud, they should exists some very strong electric field. But where does the REA occur? now they have three models, three models. The first one is they occurred above the thunderstorm. So we also have a very strong electric field above the thunderstorm, and then when some steep gamma ray and then will trigger the RIA process and then generate the gamma ray. And then the other possibility is this kind of electric field is around the thunderstorm. So the gamma ray will be triggered, not above or inside the cloud, but very near to the cloud. And then the third one is this gamma ray will be triggered inside the cloud. So this is now the three possibility we are discussing about for the source of these high energy photons. And in the coming studies now, because one possibility is that this high energy photon was generated above the thunderstorm. So the transient luminant events, including SPRI, jets, and the ELF, was suspected to the source of TGF in the early days. So, but this kind of suspicion will be eliminated the possibility soon because of the atmospheric absorption. Okay, sorry. The consideration of this kind of possibility is atmospheric absorption, because the scientists believe that if this kind of gamma ray occurred in the lower atmosphere, the gamma ray will be absorbed by the atmosphere. So it is very hard to detect a very strong gamma ray emission in the higher orbit. But the terrestrial gamma ray flash events detected by Asia, this is an Italian satellite, was all located in a thunderstorm. Its energy is as high as an incredible 100 MeV. So this they give a cartoon like in the thunder cloud, the positive charge and the negative charge in the cloud will form very strong electric field here, and some high energy electrons from a cosmic ray or from outside will trigger the avalanche process, and then generate gamma ray here, and some of the gamma ray will be absorbed by the atmosphere, but lots of gamma ray can be passing the atmosphere and be detected by the satellites. So now the new observation evidence favors intensive intercloud discharges as a source of the terrestrial gamma ray flashes. And the lightning is more interesting than we already know. This is another paper published in 2017. This is a Japan team from the Kyoto University. They deployed several gamma ray detectors around the nuclear planet in Japan, and this is the ray detectors was deployed by the planet itself. And with these detectors, they identify the photonuclear reaction triggered by the lightning discharges. So that means the lightning in the thunder cloud, and this discharge generated the gamma ray, and then the gamma ray hit the air molecule, that means the nitrogen 14, and then they generate the isotope of 13 nitrogen, and then the positron in this process will analyzation, and then with an emission analyzation. So the thunderous nuclear reaction was detected by the light curve of the detector around the planet, and successfully identified this rare isotope. And in the last year, a terrestrial gamma ray flash and the associated ELF were observed by the instrument on board Interspace Station. This is the instrument is Atmosphere Space Interaction Monitor, also known as ASIM, which is the instrument deployed by the Denmark team. The ELF is transient, ultraviolet, optical, and ultraviolet optical emission excited in the low atmosphere by the EMP, and the rate from the lightning pulse. And the duration of the ELF is very short. It's less than 1 millisecond. Its height is about 90 kilometers, and the diameter of the events is about 30 kilometers. So, according to the research issue, the ELF is a very good proxy of energetic lightning. So that means the ELF will be generated by the top 7% of the energetic lightning. So this ELF was identified to be produced by an intercloud discharge. So the TeNeP team give us a cartoon of the observation that the intercloud discharge generated terrestrial gamma ray flashes, and the terrestrial gamma ray flashes was the gamma ray photons was collected by the satellite, and then the photometers also detected the signals of the ELFs. So this story was chosen as a cover story of the science magazine, the Science Journal, and then they give a cartoon that the lightning is here, and the land will generate a lot of gamma ray photons here, and then we also have signatures of ELF. So to capture the atmosphere transient in UV band is become a new approach to explore the terrestrial gamma ray flashes, because this UV emission from ELFs is a very interesting signatures. The lightning in the cloud cannot generate such kind of emission because UV photons will be totally absorbed by the cloud and the lower atmosphere. So only ELFs will generate such kind of emission. And energetic, this kind of ELF is also a good proxy of the energetic lightning. So if we monitor the transient in UV band, so that means we can capture the energetic lightning, which is capable to produce TGF. So this is become a strategy of to explore terrestrial gamma ray flash. So this is also the very important idea we put into the DIAT as to observe the transient in UV band. So the atmospheric transient 大气瞬变现象 become a cutting-edge interdisciplinary research. And this research, we have also have some very good experience, especially for the lightning and for the transient luminous events based on the Formosa 2 and the issue missions. So this interdisciplinary research covers atmospheric electricity, ionospheric physics, and also atmospheric science and high energy physics. So in the following slide, I will talk about the space plasma. Because electron density and the temperature plays a very important role in the ionospheric physics. And the TNE will affect the shortwave communication, Earth satellites, and interplanetary spacecraft communication, as well as military and civilian satellite navigations. And the monitor on NE and the TE is also the major scientific object in the ionospheric satellite missions, including Formosa 1, 3, 5, and 7, as well as the US DNSP satellite programs. But typically, to measure the electron density and the temperature, the Lamia probe is the most traditional instrument to be used. But the traditional Lamia probe is susceptible to be surface contamination and the satellite floating potential. And this is the drawing we prepared by our team. We can see that with the contamination, there has some hysteresis, and it will also cause the distortion of the shape of our scan when we scan the voltages. So This kind of surface contamination and the satellite potential, floating potential, will cause the measurement deviation. Professor Oyama spent 5 years to develop a new instrument named as a TNET. And this instrument is a floating potential and surface contamination free. But this instrument still doesn't have a chance to put it into the space, for the practical measurement. So this is their first flight in the space. The application of the TNAP can be, I will give a very brief introduction. By substitution of Formosa 7 radio occultations observations, the ionospheric assessment model calculates the ionospheric density for 2 days with a different height, at a local time of 14 in 2 days. This is in 2019, and this is 2020. And we can see there is a similar day of the year and similar solar activities. But however, the ionospheric tides shows obvious discrepancy. We can see very clear 4-wave signatures here, but we can only see 3 here. So the TNEP can help to have a more accurate observation to help the examination models. In addition to that, now the Formosa 7 can use a radio occultation to get the electron density profiles. But with this kind of occultation, they use inversion to calculate these profiles. But if we can have some more precise observations in the upper portions of the profiles, so it can help to update the top side profiles by the Formosa 8 observation data. And the ion temperature probes by the TNAPs, and that can be also used to validate the Formosa 7 IBM measurements. And the air glow is one of the topics, especially 630 nanometers, because the 630 nanometer air glow radiance is a proportion of the electron density. So the source of the electron is in the peak is located in the ionosphere, about 250 to 400 kilometers. The vertical radiance temperature is about 10 to 100 to 200 radians already. So the observation of 630 nanometers air glow is to use to observe the peak electron density of ionosphere and monitor some features of ionosphere such as MSDID and the EPB. And the EPB, the equatorial plasma bubble, is a plasma display density depletion caused by depletion. This can be observed by TNEP in situ measurement and 630 air glow. So if we have TNEP measurements over here, and we can see the attitude of the peak plasma density is also here. Okay, so by the measurement here, we can have a cartoon here. So with the fly of a Formosa 8, we can have an in situ measurement at this position. But with the camera, we can observe the air glow with a later direction. So we can detect the plasma density depletion at the 540 kilometers altitude. And also the 630 air glow observation can be also used to detect the EPB. So some simulation was carried out by NCKU team. So this is use a semi-3 model to simulate the air glow. So the simulated air glow is assumed occurring at 250 kilometers high, and the spatial resolution about 0.21 kilometers, which is equivalent to the spatial resolution of the DIAT. So without the EPB, this is the observation, the density we can observe from the DIAT. But if EPB exists, So the density will look like this. So with this simulation, we can figure out that the DIAT can have the capability to detect the EPP occurrences. So for the mission objectives, in this mission, we have listed 5 scientific objectives. So with the long-term global monitoring on about the energetic lightning and the TLEs in ultraviolet and the visible wavelengths. And we also want to collaborate with other fluorine gamma ray satellites and to conduct a joint observation to understand the physical mechanism of terrestrial gamma ray flash. And then we can also do the air-glow observation and the global ionospheric light density and the temperature monitoring. And the observation data in this mission can also use to improve the uncertainty errors in the inversion of upper layer of Formosa 7 occultation observation. In addition to scientific objective, we also hope to have an independent design and the manufacturing space-grade scientific instrument, and to cultivate the young talents in space science and engineering. So therefore, we will try to grab a lot of young guys, including undergraduate students, master and the PhD students, and the postdoc to join this mission. So in the following slides, I will give us some introduction to about the instrumentation. Now for the scientific panel, there are 3 major units. The first one is DIAT and the TNEP. This is the sensor parts. And the other one is we call SPU. This is a science panel electronics unit. And it will handle the data collected by DIAT and the TNAP and to do onboard processing and to transmit the data to the satellite bus. So this is the system functional block diagrams of the whole system. So you can find here, this is the main parts of the SPU. We have an FPGA and we also have a processor to do the data compression modules and the camera control unit. And then we also equip it with magnetic MRAM as the storage area. And we have equipped with 2 camera head and with provided with some bias voltages and high driving voltages. And this is AD converter to convert the digital signals, analog signals from the CCD chip into the digital output. So here is the DIAT. The design of the DIAT is a heritage of the DACAM, which is on board the RISET, the Japanese RISET microset, which has been successfully launched in 2019. So this is DACAM we placed on the Japanese microset. And with this camera, have some very interesting feature because it will equip with lossless compression. The data compression ratio typically is greater than 2.5 and it can reach to 4. And this is a very lightweight camera and with a very low power consumption. And this camera is also have onboard processing to detect the transient. So we can compress images and his successive images to detect the possible transient. So with this camera, we can already successfully use to detect the lightning and the transient. But in the DIAT, several improvements and new functions are used to elevate his scientific performance, including we use UV-CCD, and we have autonomous optical design and the modular design. And in this camera, we also have a participation from the local manufacturers, including filter, mechanical shutter, optics, lens, and the flight software. So I give us some brief introduction about the improvement of this camera. Because the CCD chip T065 used in DACAM has been discontinued. And not only to be discontinued, but this CCD also have a small size and very limited spatial resolution. So in this mission, we use a new CCD from manufactured by Hamamatsu. This CCD is non-cooled and with a back-illuminated thin CCD. The pixel size is 512 by 512. The chip size the pixel size is about 24 microns. This QE is very impressive. It can be up to 90% at about in the blue light. But through spatial process and the technology, this CCD have a very good response in the blue end of the spectral, the QE curves. The blue end can reach to 200 nanometers. So that means this chip can have capability on about the UV images. But unfortunately, they only sold the user with a chip, but the user have to develop the driving and the conditioning circuit by themselves. So that means other than T065, we should spend a lot of time to depend on his drive circuit. So this is the effort by our engineers. We have successfully developed his driving circuit and the conditioning circuit. So the analog and the firmware for I/O control has been successfully developed by NCKU team in the past years. So we have the full capability to manipulate this CCD, to take the pictures, to read out, and to display, and to do any control on about the gain and the shutters. And we also, in the previous missions, the cameras here is a commercial one. But the commercial cameras, the commercial lens cannot satisfy the requirement of the DIAT. So we have to have develop our own capability for the optical design. But it is very challenging in optical design of ultraviolet band because of shorter wavelengths, only 1/3 of the ray light. And the other very hot topics is about conventional, the material for this kind of optics lens. Because a conventional BK7 glass will absorb the UV light. And this conventional glass cannot be used as the material of the lens. But we have to use the others like the quartz, fused silica, or magnesium fluoride as the UV optics. And the CCD size in this mission is much larger than the previous one. We can see in this mission, the size is about 12.3 millimeters, but in the original one, only almost 5 millimeters. So in this mission, we have the independent optical design and the fabrication capability. And this is also a necessary transformation for NCKU team. And the other thing is about the modular design. Because the test of the DIAT unit has to be carried out simultaneously, because we have 2 cameras in a box. But the DIAT is an independent camera modules. You can see here, this is an independent camera module, including filter, lens, CCD, and the shutters. So these modules can be tested independently. So the test, focusing, and the calibration can be carried out separately, and then it reduces the difficulties on the design and the integration as well as the test. Furthermore, this module can be installed directly on CubeSats in the future. But not only to the design and the fabricate, but also we will face a very challenging issues on about the UV optics in the labs. Because of the traditional glass and the optic system cannot be used for UV optics because of the absorption. And the radiation of the UV will harm to the operators. So therefore, in the past years, we have purchased several instruments and facilities in our lab including the UV light source. It is a deuterium lamp. This is the spectrum of this lamp. It can produce generate some the UV light for our calibration. And then we also upgrade our photometers to have a UV, the UV photodiode. This is the curves of the filters. And then we also have more parameters with modified UV sources. And so it can generate the light for our calibration. And then we also prepare the fused silica UV lens for the optical calibration and the test. And for the TNET, this is the improvement of the ETP on board the Russia Tatiana microstat. And it is, as I mentioned, it is developed by Professor Oyama during his stay in NCKU. Originally, his main scientific goal is to be able to accurately determine the small variation of the NETE as an earthquake precursor and determine the epicenter. But we can use this instrument to do the global monitoring and the other scientific object. So the design of the TNAP is done, and the prototype has finished the test in our space plasma chamber. I will show the picture later. And this is the ETP, originally installed in Tatiana too. And this instrument is a highly mature and a tiny space instrument. And this is a PCB board, and this is an electron. Originally designed for the Tatiana, but we modified this electrode for TNEP as a square shape. So for the TNAP, we use measure the floating potential, the offset caused by a single frequency, a radio frequency signal. So it is in this experiment we ejected a 200 kilohertz signal, and we operated this one in ETP mode. So with this single frequency signal, we can measure the electron temperature. And on the same circuit, if we put it into a sweeping radio signals and apply to the electrode, the floating potential offset caused by the upper hybrid resonance can be measured to determine the electron density. It is we call the IP mode. So with this instrument, we can have a very similar circuit in the output. But the only difference to measure the NE and the TE is its RF circuit. This is the original design during Professor Oyama's stay in NCKU. And then we modify this RF circuit to a very simple direct digital synthesizer. We call also named as DDS. With this DDS, this one will become very simple as a chip. So the TNAP, in the TNAP instrument, the floating potential offset will not be affected by the satellite potential. So it can overcome the potential drift of the laminar probe, which is caused by a very limited satellite area. Okay, so TNAP can measure the TE and the NE with a higher accuracy. So this is an experiment we just have done last week in our space plasma chamber. We have a space plasma source here, and then we place a laminar probe here for comparison, and we place the TNAP here with two kind of electrode. And then we can see here, this is when we release the plasma, when we turn on the sweeping voltage, sweeping frequency signals, we can see the signal changes here. So it is this instrument has successfully, the prototype has successfully passed the test of the ETP mode. So in the coming months, we will carry out the following environmental tests, including the servo cycle test, which will be done in physics and the ASTRC NCKU, and the thermal vacuum test at the EE NCKU, and the vibration test at the ASTRC NCKU, and the EMC EMI test will be assisted by AIDC. And then we also do the vacuum test at the ICEPS NCKU or ASTRC. And then the performance test of the DIAT will be carried out in physics and the TNAP will be ICEPs of physics if our new chamber can get ready soon. Okay. And in this slide, I also has mentioned that in this mission, not only to give a chance to the young talents to participate in the space mission, but we also hope to can have more Taiwan local companies can join the space market. So in this mission, we have a lot of participant vendors. The optics are from the control optics, mechanical shutters from this company, and the filters from the ETA film. This company is also our vendor in the DIAT instruments. And the flight software will be collaborated with this called tag system. And the PCB will harness, and the EMC AMI test will be assisted by the AIDC. And the machining will be by this company. So I will give us some very conclusion about my presentation today. The DIAT and the TNAP are heritage improvement of existing space instrument. So therefore, this is basically they are very mature, and then we also put a lot of new enhancement, and the new functions. The scientific objective proposed in this mission are very challenging, but this is not a new science to our space community. They are based on the scientific achievement of Formosa 2 issue, Formosa 3, and the Formosa 7 missions. So the scientists in this mission have experience about the scientific objectives. And it is also cutting edge disciplinary studies of these fields. So we can expect a good collaboration among the scientists in this field. So in addition to the scientific objectives, we hope to have more colleagues, engineers, and the young talents cultivated in this mission. And then we also have to expect the collaboration with foreign missions and the foreign teams. And the collaboration with local vendors can also accelerate their entries in the space market. And finally, I would like to thank for the great support from the Chen University and the National Space Organization. Thank you. That's all my talk today. Thank you for your listening.
Thank you. Thank you for being calm while the fire alarm was on. So any questions from audience? So I have a quick question that do you have any possible coordination with the following talk that we're also working on the high energy physics of the gamma ray? Are there any plan, or are there any discussion, or you will do so in the future?
Yeah, I'm looking forward to collaborate with the team with gamma ray detectors in this mission. So it depends on about the sensitivity and the capability of the gamma ray detector. At least I know we have already sent a message to ASIC, the Denmark team, to ask a collaboration, and they will have a very positive response. And we also have expected with a collaboration with another French team. Their satellite was just launched last year. And if the NCKU team, their detector can provide the capability to detect the terrestrial gamma ray flash, I'm more than happy to collaborate with them.
Okay, any other questions from the audience?
Alfred, just your measurements, are they on all the time, 24 hours a day, or you have some, because you are doing many different things, or you have a different, let's say, modes. This time you're doing this kind of measurement, that time doing that kind of measurements.
Yeah, I suppose it will become an art to arrange the operation of this mission. Because the time is very limited, we only have can be allowed to operate in the night time. And you can see all the objective listed can be operated in the night time. But at least when we enter the eclipse, we will turn on the TNET and correct the data of the NE and the T data measurement all the time. But for the operation of the images, it depends on about the orbits and the requirement. For example, for some orbits which is will not cross to the lightning active region, we can use this program, configure these images to observe the air glow, something of like. So I suppose the mission program, the configuration, and the mission planning during the mission will become an art, not a fully science.
And Carl asked the question before. I think that the idea is that whether for Formosa 8 mission now, you have a science team, and you have one single experiment on the spacecraft, right? So you are the science team on the Formosa 8A, and the other one, by Professor Zhang, is on the Formosa 8B. But you're also talking about a possible coordination, simultaneous observations. Would there be a kind of like a joint science team for the first two spacecraft?
Pardon, sorry, the last portion of your question cannot be clear here. Sorry, maybe network.
I was saying that whether there would be time that your experiment and Professor Zhang's experiment could, the experimental team could stick together to coordinate the measurements.
Yeah, I suppose this is very important to sit down to have a coordinated the operation of the mission. But I think at this phase, now both of the NCKU and the NTHU are busy for the development and the fabricate and the test of our instrument. So this issue, of course, it is important, but we can talk about it maybe later. I suppose we have to talk about it, but maybe not at now.
So later means the 6 months from now?
I suppose no. I suppose after critical design review, all the performance and the parameters of the instrument has been nailed down. So I suppose it is maybe a good time to start the discussion about the collaboration and the mission planning. The future, because this mission is going to be launched in 2023, and the payload will be launched in 2024. So I suppose maybe after the critical design review, maybe a good timing to discuss it.
Okay, good. Yeah, I think that the NSPO should plan on that too. Yeah, thank you.
Yeah, just I want to make a comment why it should be important, because when you look at the air glow, a red line, and you see the brightness, and I was wondering that a lot of reasons can cause the brightness in the air glow, not just only the gamma ray. So having the other exact gamma ray observation can help you to identify the events. So that'll be something. But it's true that it's not necessary at this phase. We talk about that. That would be when both satellites are on orbit, checking the data are in good quality, and then this kind of a cross comparison study can be done, or check can be done. Yeah. That's my suggestion. So do we? So I guess we are already at 12. So thank you, Alfred, for bringing up this very excellent talk. And we will proceed to the next one by Professor Zhang.